Born in 1546, Tycho Brahe was a Danish aristocrat, alchemist, and the greatest astronomer prior to the discovery of the telescope. He was born to a prominent Danish family and studied at many universities throughout Europe. After his father's death in 1571, Tycho bought a laboratory in his uncle's manor to dedicate his life to alchemy. In 1576, King Frederick II offered Tycho an island near Copenhagen and supported the construction of a feudal manor where Tycho could create his own observatory. In return, Brahe would be expected to provide the crown astrological advice and carry out several minor administrative duties. Over the course of 5 years, Tycho created a Renaissance villa named Uraniborg, the Castle of Astronomy. The Uraniborg housed a library and served as an observation platform for various devices that Brahe had designed for measuring the fixed angular coordinates of the stars and locations of the sun, moon, and known planets as they moved irregularly through the star field. This is when Tycho realized the errors in astronomy at the time originated from poor data. Tycho aimed to reform all astronomy by improving the precision of his instruments and using new methods for computing accurately. Tycho's efforts paid off immensely. It is estimated that his data was twice as accurate as any other information gathered during the time period. This impressive data set the stage for Johannes Kepler to publish his 3 laws. Kepler was born in 1571 and went on to become very talented in mathematics. In 1596, he published Mysterium Cosmographicum, which contained the origins of his future mathematical explanations of the universe. Brahe read this work, and was the reason he invited Kepler to study with him in Prague. Although the two did not get along so well, Kepler realized Brahe's value and stuck with him until his sudden death in 1601. Kepler then inherited Brahe's meticulous data and set out to fit the data into a model of the universe. Through Brahe's work, Kepler theorized 3 laws that dictated planetary orbit. He published Astronomia Nova and Harmonies Mundi, which contained these laws. His first law rejected previous thoughts of circular orbits. Kepler stated that the orbit of a planet moved as an ellipse, not a circle. His second law stated that the velocities of the planets are not uniform, but vary at different points in their orbits. The areas swept by the radius vectors in times are equal. The third and final law dictated that the velocities of the planets relative to each other can be expressed mathematically. The squares of the period of revolution are proportional to the cubes of the distances from the sun. Kepler's laws can be really difficult when talking about them theoretically, but when you look to the skies, they can make a lot more sense. Kepler's laws can be difficult to understand unless you see how they're actually applied in the real world. So if you look through my technologically advanced telescope, you can see a planet right here, which in this case is Mercury, and the Sun, which is a large mass that Mercury revolves around. So an ellipse is made up of 2 focal points, and in this case it is the Sun, which Kepler's law states, and then the other one is over here. And as you can see, the planet revolves around the Sun as an ellipse, not as a circle like previously thought in the time period. Kepler's second law talks about sweeps of a planet's orbit. So for simplicity's sake, think of a sweep as like a pizza slice of an oval-shaped pizza. So when you monitor the area of the sweep that a planet does over a certain amount of time, the areas of those slices will be the same. So if you monitor the area of a sweep for a quarter year, you can see that all of these slices are actually the same area, even though the velocity of the planet does not remain the same throughout. As you can see, as it gets closer to the Sun, the velocity increases, but the time period was the same, so therefore the area of the sweeps remained the same. Kepler's third law refers to the mathematical relationship between the period of a revolution of a planet and its average orbital radius. So in this case, our average orbital radius of this planet is 2 astronomical units, and the period is 2.83 years. So if you square the period, that is equal to the average orbital radius cubed. So 2.83 squared is equal to 8, as is 2 cubed. The importance of Brahe and Kepler can never be understated. for their research has been used by people such as Isaac Newton and even scientists today.